Can you hear me okay? Good. All right. I'm Steven. I'm going to be presenting some work that I did with my advisors, Steve Zdancewic and Osbert Bastani, on optimal program synthesis by abstract interpretation. So to start off with, there's been a lot of recent interest in using program synthesis for data science, like end-user programming sorts of tasks. And so for instance, biologists often have a lot of video of animals, such as mice interacting, and they might want to identify when the mice are engaging in certain behaviors. Or a fisheries regulator might have a lot of vessel tracks, and they might be interested in looking for suspicious behavior that might be indicative of illegal fishing. Or an autonomous driving engineer might have video of a traffic camera and might be interested in rare driving behaviors that they need to account for. So focusing on this example a little bit, suppose I'm an autonomous driving engineer and I've taken many hours of video from this traffic camera and I've run an off-the-shelf object tracker. And I've gotten these tracks that I've put in red. And maybe, as an example, I'm interested in finding cars that make this particular turn. Like, how would I go about doing that? How would I go about bringing them out of all of these? Well, I might sort of draw these two lines in blue and in green, and I might sort of say, the cars I'm interested in are the ones that at first are in the blue lane, then anything happens while they're making the turn, and then they're in the green lane. But really, I've just drawn two lines, so I can't say that. I have to say something more like, the distance between a car and the blue line is less than some threshold theta 1, and then anything happens, and then the distance between the car and the green line is less than some threshold theta 2. And this is a challenging problem, because even if I'm an expert, I can't necessarily just look at the video and say, oh, it's like 20 pixels is the right threshold. So how would you do it? One thing you could do is you could synthesize these parameters. And for good measure, we're just going to synthesize the entire programs from labeled data. So we have a set of, in this case, trajectories of cars, x, a set of human labels, y, and we're trying to find a program such that when we evaluate the program on each trajectory, we get the human label. There's another problem, though, which is that if this is labeled by a human, you might make mistakes, and the data is very fuzzy, and so it may be impossible to actually do perfect classification. So instead, we want to do optimal synthesis, where we have some objective u, say accuracy, or in our implementation, and in practice, you might use something like F1 score. And we're trying to find a program P that maximizes the accuracy, for instance, of its predictions. There is other work in this area. There is some work called NEAR, which uses gradient-based optimization methods on this problem, but it doesn't have any optimality guarantee. And there's prior work on optimal synthesis using SMT solvers, but that work isn't really focused on these sorts of objectives. It's focused on rather different sorts of objectives, and we compare to this work. So in our work, we're trying to find an efficient, optimal solution to this optimization problem, and we do so by using abstract interpretation to construct a search heuristic. If you're familiar, this is actually an admissible A-star search heuristic, but it's okay if you're not familiar with that. So in the rest of this talk, I'm going to review the sort of standard technique of enumerative synthesis. I'm going to show our algorithm, including introducing notions of generalized partial programs and abstract semantics. And I'll show our implementation on two different existing domain-specific languages, and finally an evaluation showing orders of magnitude speed up over the SMT-based approach. So jumping into a concrete example of a synthesis task you might want to solve, suppose I have two car trajectories, x1 and x2, and each one's a sequence of frames, so maybe x1, on the first frame, the car is 0.75 from the lane. It also has some velocity, some acceleration. There are subsequent frames where maybe the distance is 0.5. You have another trajectory. And I, as a human, have labeled the first one true, an instance of the behavior, the second one false, not an instance of behavior. So the language that I'm going to be using here is sort of like regular expressions or temporal logic, where you might have predicates like the distance is less than theta or the distance is greater than theta, where here theta are real numbers between 0 and 1. You might also have conjunctions, disjunctions, or sequencings of these programs. And for concreteness, I'll be focusing a lot on programs of this form, where the distance is greater than a threshold, and then the distance is less than a threshold. And so the semantics of these sorts of programs are that they map trajectories to Booleans. And so for instance, maybe if we have the parameters 0.2, 0.1, the semantics on the x1 are false, and maybe on x2 it's also false. So now we have our predictions. And so now we have our objective function we're trying to maximize, and that's a function of the predictions, which is sort of Boolean to the n, and it maps those to a real number. And so, for instance, accuracy of some predictions y prime with respect to ground truth y, or just the number of places where these labels agree, divided by the size of the data set. And so if we're evaluating the accuracy of this particular program, we know that it outputs predictions false, false, and while those differ from the ground truth on x1, it was supposed to be true, but agree on x2, and so we get accuracy 1/2. So to reiterate, our goal here is to find a program that maximizes the accuracy of its predictions on the data set. So how would you typically do this? A standard approach would be using enumerative synthesis, where you have your grammar, and you actually augment that grammar with a whole, which I'm writing question mark, question mark. So these are our partial programs. And now you can form a search tree, where the initial node in the search tree is just a whole, and then the children of each node in the search tree are what you get if you fill that whole with productions from the grammar. So for instance, you might have distance less than some threshold, or you might have whole and whole, or whole then whole. You can kind of continue this process until you get down to this example we saw before, where we have distance greater than some number, and then distance less than some threshold. The sort of programs beneath this can be parameterized by this unit square of parameters, theta 1 and theta 2. And so one thing you could do, you could just sort of do a grid search. You could just pick a dense grid of points, and now you have concrete programs so you can evaluate them. So for instance, maybe if we have point 0, 0, we'd get the predictions false, false. We already saw the accuracy was 1/2. You can continue that. Maybe eventually you get some different predictions, say false, true. The accuracy would actually be 0. You continue until maybe you get accuracy 1. And then you've evaluated all these programs. The challenge here is this is a really high branching factor for our search. Like this was a branching factor of 100, and we can't really say usually for sure that we're done until we've considered almost every program in the space. So we want to do better than this. And the key insight here is that partial programs represent nested sets of concrete programs. So what do I mean by that? Well, this whole sort of represents the set of all programs, whereas distance less than whole represents all the programs that are distance less than followed by some concrete number. Or conjunction and sequencing of wholes are all the programs that begin with a conjunction or begin with a sequencing. And these sets of these children, they actually form a partition of the set of their parent. So these are all the possible ways that you could fill that first hole. And you can also sort of drill down all the way to a concrete program, and you find that this path is a decreasing sequence of sets that converges to a concrete program. So if we focus on this area that was causing us trouble at the high branching factor, what we're going to do is, rather than branching directly to these concrete programs, we're going to use some sort of interval constrained hole, which will give us more structure on our space. So in particular, we'll introduce a new construct to our partial programs, which is that of a bounded hole. And what that's supposed to represent is just all the programs you get by filling that hole with a number inside the interval. But this sort of lets us have a more structured space, because now rather than branching 100 times, we can divide the space into, say, 4 quadrants, for instance. We kind of do some kind of bisection in 2 dimensions. And so now, say, this first node would represent all the points between 0 and 1/2 and 0 and 1/2, and similarly for the other ones. And just like before, these children are a partition of their parent. The 4 quadrants partition this unit square. And we can also sort of iterate the process where each of these regions can now be subdivided into 4 subregions. We continue until we get arbitrarily close to a concrete program. But now that we have these constrained holes, we might hope to be able to do some pruning on the search space. In order to do that, we're going to evaluate these programs, which these generalized partial programs I'll call abstract programs. And for concreteness, we'll consider Q sharp, sharp as in it's an abstract program rather than a concrete one. And where before the semantics of programs were Booleans, now the semantics are going to be abstract Booleans. So false, true, or top, where top represents sort of non-deterministically false or true. So now the semantics, rather than returning Booleans, is going to return abstract Booleans. And now if we evaluate Q sharp, we might see it predicts false on the first trajectory, and it returns top on the second trajectory. So our objectives before mapped a set of Booleans to a real number. Now we're going to map these abstract predictions, these abstract Booleans, to an abstract real number, where the abstract real number is, for our purposes, just a real interval. So we had accuracy. We need an abstract notion of accuracy. In this case, I'm just lifting all of the arithmetic operations to be some kind of interval version of themselves. And finally, we consider the abstract accuracy of the abstract program Q sharp. And here we saw that the predictions were false and top. Well, it output false, the ground truth is true, so we definitely got the prediction wrong on x1, but we outputted top for x2, and so we sort of said we don't know. And so the accuracy definitely isn't 1, but it could be anywhere between 0 and 1/2. And the guarantee that we actually have is that for any concrete program inside of an abstract program, the accuracy of the concrete program is going to be contained in the abstract accuracy interval of the abstract program. And so now what this is going to let us do is it's going to let us use the upper bound of this abstract accuracy that we get out of the abstract semantics as a search heuristic. So in particular, we take the upper bound, the supremum of this abstract accuracy, and this will let us prioritize the more promising areas of the search tree. So if we're back here, what do? Well, we evaluate our abstract semantics, we compute our abstract accuracy. Because it could be any point in this parameter space, unsurprisingly, we would return top for an abstract accuracy of 0 to 1. So considering that upper bound and plotting it over here, we'd see, well, all the points, all the concrete programs in this blue region have accuracy at most 1. That's not that informative, so we'd continue search. So then if we consider this one, we might output false top. And we already saw that the abstract accuracy there was 0 to 1/2. And so now we know that all the points in this purple region achieve accuracy at most 1/2. We could sort of continue. We'd see these regions are also at most 1/2. This last region, well, it outputs the prediction false for x2, which is correct. So its abstract accuracy is going to be between 1/2 and 1. And so now intuitively, it sort of makes sense that we should pursue this region first. It could be that the optimal program lies in the purple region, but that's only true if the best accuracy we can get is only 1/2. Whereas as far as we know, you could have something better in the blue region. So we could expand that. We could compute the abstract accuracies. And in this particular case, we'll see that we have these two blue regions with abstract accuracies 1 to 1, which guarantees us that any point we pick in those regions is going to have a concrete accuracy of 1. So in fact, in this case, we know we can just pick anything from those regions and we're done. We've found the optimal solutions, and we don't even have to consider the rest of the search space. So this is our algorithm. We implemented it on 2 different domain-specific languages, the first of which is from some prior work called Quiver. This is actually the language that I was just showing you. It's sort of regular expression or temporal logic style. There's prior work called Near, and they have a DSL that's much more map-fold style, where they manipulate lists. And finally, we consider the F1 score objective instead of accuracy. This is a more realistic metric that's used in classification tasks. But the naive abstraction you come up with by just looking at the arithmetic formula and plugging in abstract transformers there doesn't actually work well, and we're able to derive a better abstraction. We evaluate on these 2 different languages, and on the Near language, we use their data set, which has 2 mouse behavior classification tasks. On the Quiver language, we have 6 mouse classification tasks and 10 traffic classification tasks. We compare our approach to the SMT-based approaches, as in metasketches. We consider how the time it takes to find the optimal program changes as a function of data set size. These plots are log, our approach is in blue. As you can see, we do several orders of magnitude better than those approaches. We also consider the ablation, where we use breadth-first search instead of a heuristic, and find that the heuristic search is indeed important. So to conclude, in this paper, we efficiently find an optimal solution to this optimization problem by using abstract interpretation to construct an admissible A-star search heuristic. This happens over a space of generalized partial programs, and it's orders of magnitude faster than prior SMT-based optimal synthesis approaches. And we evaluate on 2 existing DSLs for data classification. So, thank you, and I'd be happy to take your questions.
Hi.
Hi.
Nice talk. So if it terminates, then you will have the optimal solution.
Yeah.
What if it does not terminate, or if you have some time budget, you have to stop, then...
Yeah, it's actually very conducive to some sort of online thing because you have your search frontier, and for every item in that frontier, you have abstract bounds, and so you indeed get a lower bound as well. So in fact, in the experiment I didn't show, we do sort of have that where you can kind of over time like terminate early, and you'll at least have some sorts of upper and lower bounds.
Thanks.
Hi. So your initial motivation was more like an unsupervised learning problem in the sense that you might want to look at abnormalities of some kind.
Yeah.
I'm sorry.
Or no, go ahead.
So I was just wondering whether you have any ideas on how I could just find anomalous behavior by not giving any information at all.
So we do consider supervised learning just like the very small data regime. So in all this, we sort of assume that, like in some of them, there are like 2 labeled positive examples from a user and 10 negatives. So it is supervised in that sense. It's just like synthesis makes it very data efficient, and that's important. In terms of finding anomalous behavior, I think there's probably a whole literature in machine learning for that, and maybe this could be plugged in there, although I haven't studied that myself.
Okay, thanks.
Hi, great talk.
Thanks.
So do you have any issues around either loss of precision from the abstraction in the interval domain, and or kind of limitations due to kind of the dimensionality growing? I think if you're doing this kind of partitioning, it might not scale very well beyond a few dimensions.
Right. So I guess one thing that I maybe didn't emphasize is you can kind of plug in any abstract domain from abstract interpretation you want here. We did, in our experiments, use this bisection domain that I showed. And because the program through the synthesizing didn't have that many parameters, it actually worked like fairly well. But I mean, definitely there are still scaling issues to any of these things where you're dealing with these exponentially large spaces. Yeah, and I mean, one thing that's important is that your abstraction be like fairly good. If your abstraction is too loose, you just sort of degenerate to breadth first search because your upper bound is trivial. And so that, I think, is maybe a point where it might be tricky if you're trying to adapt to a new domain, is you have to make sure that your abstractions are sufficiently tight.
Oh, hi. So in your example, you kind of split your interval in half. I guess that choice of splitting, I was just wondering, in other domains, there's like different ways you can split. Like maybe you split, yeah, you might use a gradient-based thing to split based on that. I'm just wondering, how do you choose, I guess, maybe any insight on why that works particularly well as opposed to any other kind of choice of partitioning?
I think like, if you don't know anything else about your parameter space, like if you have a prior distribution, you might want to do something like split in half based on probability mass. In this case, we didn't have anything like that. We just basically had a square, and in some sense there, the simplest thing is this like binary splitting. But yeah, if you have other knowledge, you might want to split differently. You could split into different numbers of things. And indeed, you don't have to use these kinds of square abstractions. You could definitely use, I mean, I haven't actually implemented it or evaluated it, but at least theoretically, you could use something like vector space abstractions or polytopes or something like that.
So I have a question here. So when you selected the benchmarks for this neuro-symbolic programming, what was the kind of properties you considered in this kind of domains? And is it applicable in the same way for the other domains? Do you have any study here?
I guess the sort of important properties are the ones that make it work particularly well are first of all, like you need some kind of large space probably of constants. And so for instance, these real parameters are like a very good use case for that. And the other thing is you need to have like some quantitative objective you're trying to optimize. And so I mean, a lot of synthesis tasks, you're trying to satisfy a correctness specification. I mean, this would be really degenerate. It would kind of work, but it would just be true-false. You'd just be rediscovering like deductive pruning. And so I think the things we've been considering are ones where you have these like real valued constants basically, and this quantitative objective that you're trying to optimize. I don't know if that answers your question.
Yes.
Thank you so much.
If there is no more questions, let's thank the speaker.